Good morning, everyone. My name is Truong Son. I come from Vietnam. At the moment, I'm a second year bachelor student at the university. Today, I would like to introduce to you my thesis, which is semi-supervised adaptive facial checking method. My supervisor is Dr. Lorin Andras. The presentation will be separated in 5 parts. First, I want to talk about what a facial checking problem is. This problem is to find 49 facial landmark. Why is this landmark important? First, with this landmark, we can extract human face features, which is important for human facial recognitions. And second, with this landmark, we can use machine learning methods, for example, support vector machine, neural network, to classify emotions. Computer is not humanized, so computer needs algorithm to extract features. In the field of computer vision, histogram-oriented gradients is very widely used. It was invented by Dallas and Pinchicks from Massachusetts Institute of Technologies in the CVPR 2005 paper. In our experiment, we find that the pack size 24 by 24 gives the best result. The idea of hope features is just to find the gradient in a localized area. That means we need to find the directional changing of grayscale in the interesting area. To find human face features, first we apply biological algorithms to find the rectangle covers the face. This algorithms is obtained in OpenCV library. Given a facial landmark, in each landmark, each point of landmark, we extract an interest area. And with each interest area, we use histogram-oriented to find the features. Connected all features together, we get the most important features of human face. Our idea will be separated in 2 parts. The first is supervised chaining. In the supervised chaining, we use supervised descent method and sequential linear regressions to find the best possible estimated landmark by hook descriptor. And the second part is unsupervised self-improving algorithm. During real-time applications, we expect that with a large number of good chaining samples, we can improve the quality of the facial checking. And we use online procedural inverse update method to update the current linear regressions. SDM supervised descent method in the facial checkings were first proposed by Truong and Latre from CMU 2013 CVPR paper. We are given the facial images DI, the graduate landmark X star, and delta X is the distance from the starting landmark to the graduate landmark. At each landmark, we extract phi, that means hope features, and we need to map from the set of features to the distance by a linear regression. That means the matrix R. To solve this problem, to formulate this problem, we use the sum of all norm 2 square arrow. Fortunately, to find out, we have Gaussian inverse solutions. This Gaussian inverse solution of SDM is stepwise chaining, linear in each step, but non-linear in more than one step. To find the starting landmark of SDM, we average the coordinate of all landmark over the whole chaining database. For example, in this day I plot the distribution of all landmark. The red point represents the average of all landmark. In SDM chaining, for example, in this case, the green dot represents the starting landmark, as we found as the average landmark over the whole training database. The red dot is the ground truth landmark. The white arrow represents delta x, and SDM learns delta x by sequential linear regressions. SDM check-in. First, we start with the starting landmark. We extract the feature, the whole feature in this landmark, and we apply the linear regressors we trained before to move the landmark to new positions. For example, on the right hand side, you see that from the green dot, we move to the new position, the red dot. Continue with that new landmark. We start to extract the feature again, apply a second linear regression, and move to the new landmark, and so on. And final step, we convert the SDM to the root position of landmark. But SDM is not always perfect. The reason is that for example, with black skinned people, it is too difficult for histogram oriented gradients to extract the feature from black skinned people. For example, this woman on the left, the eye corner, the left eye corner is not correct. Or this man on the right, the mouth corner is not correct. And very fortunate, we have an algorithms to improve the quality of the linear regressions. Obium online pseudo inverse update method proposed by Stripe and Taptions in extreme learning methods in 2013. It is a simplification from Griffin's method based on Pufaknik's matrix inversion lemma. This is the idea of our algorithms. Here we have some notations. First, we have the sets of original landmark, original matrices, that means the linear regressor of SDM, and we have the adaptive matrices, that means the improved, the updated matrix from Obium algorithms. Here is the Bashir code of our algorithms. The first line, we suppose that t from 1 to infinite as a time series during a green time application. Line 2 to 3, it is the initializations of the algorithms. Line 5 to 13 is the SDM algorithms. First, we extract features. After that, we update new landmark. Here is the adaptation of Obium. We have the best estimated landmark found by SDM, and as this new training sample, we update our linear regressors from line 15 to 19. For examples, in this case, the left eye corner of this woman is improved. You can see that with the red dots represent adaptive checking, it improved. To estimate the error, we use root mean square error, and we see that for the whole error of phase, it improved. And for eye corners and mouth corners also. And for this man, the mouth corner is corrected, and the whole error is reduced. To test the algorithms, we have 5 different databases, 3 for training and 2 for testing. Testing on Binghamton, Whisper, 4-dimensional spontaneous facial expressions database. On the right-hand side, we had the cumulative error distribution curve between SDM and our unsupervised adaptive checking method. We can see that the y-axis is the data proportions, and the x-axis is the error. The curve moving to to the left, the better performance of the algorithm is. And on the left-hand side, we have the table of own experiment. For example, the column represents the number of samples for the adaptations, and the row represents the number of iterations for STM, and we can see that the adaptation really improved the result. And also we test our algorithms on multi-view-based database. This database to find the head positions when the eye looking. And we see that on the left-hand side, STM has some arrow with the eye corner. And on the right-hand side, our adaptive checking corrected that arrow. For the future research, with the help of Unity technologies, we can create 3D database with many hedge angles from 3D images, and we hope that with larger database it still can improve the quality of our algorithms. Conclusions. So we have seen that more precise results at corners, and this improvement is a key success of the algorithms. Secondly, fast and efficient unsupervised checking, and it can quickly adapt to the environment, for example, light, background, and the most important is that it can personalize subject during real-time application and without any additional data. That means without any human interactions during real-time applications. Finally, I would like to thank my supervisor, Dr. Lorin Andras, and all my teammate member. And I also want to thank two reviewers who gave me very good comments. I will try to fix my mistake and improve the result in the future. Thank you very much for listening.
Thank you very much. Also, yeah, colleagues, have you got any questions? Yes, please.
Yes, I do. So you mentioned both the training database and the test database. How big were databases?
Yes, for the whole training database, we have 200,000 images. 200,000. And on the testing, we use 13,000. Yes, and because we work with Carnegie Mellon University and we share the newest database, testing is the newest database with that team.
Okay, thank you.
Can we see again the images where the algorithm is wrong? Included by the valve or the I just want to understand because the measure of the HOD, so it's a histogram gradient, it's very specific, and it's hard to imagine how can it make such a big mistake, for example at the left eye, because the contrast of the eye is very big, and if you make a histogram of gradients, you could not just make such a big mistake. So what's the reason that the algorithm makes mistakes here? This is my first question.
Yes, because in the training database we have only Asian or white skinned people, and the changing of
yes, but the eye is
yes.
more lighter than the skin in any nation. I mean, independent of it's a black man or Asian or European, it doesn't matter because the eyeball is white and the around the area is darker. So I just don't understand why it doesn't fixes that
yes, you're right.
So I just maybe the window size is too small, or I don't know. So I just understand this problem.
Yes, I think that the problem is because of the training database, because we have a lot of humans, and it cannot cover all face in the training database, and maybe it's because of the training database.
My second question is, so you use this HOG, which is quite simple, but there are more sophisticated local image descriptors. Did you try any, or did you find any other in the literature which could be applied in this case?
Yes, it could be shift features, skin variant, intensive. Yes.
Sorry, and what would be the advantage, for example, of the shift features?
The shift features is it's very slow. very slow compared to.
But this is another advantage. What would be
The advantages, not a
advantage?
disadvantage, but better to say.
I think that ship is more general than the whole features, and it can choose. I mean more specific features from the whole feature. It's more general than the whole feature, but of course it's slower, much slower. Yes, please.
Did you try to separate like the white skin and the black skin training databases, because it's quite easy to detect, and then train different models for the two classes?
Yes, you're right. And actually, we do not change separately for black and white people, but we test our model on separately on the black skin people, and it improves.
Why couldn't you train separately?
Yeah, yes, you're right. It's a very nice idea, but we haven't tried it.
Have you got any questions? Thank you.
Histogram of gradients features very useful for face detection, but it's also much slower than the Viola-Jones integral image-based features. What did you find? Is it fast enough for real-time tracking?
Actually, when we implement it in C algorithm, CMax, you know it, the whole feature can extract 200 images in a second, compared to
With what image resolution?
with normalized 300 and 5300. It is not a big one, just 300.
Thank you.